Hello students, welcome you all to week 11 NPTEL problem solving session for the course Introduction to Group Theory. I'm Priyanka Sharma, the NPTEL PMRF teaching assistant for the course. I'm a research scholar from the Department of Mathematics, IIT Patna. In today's session, we will study about the symmetric group. They're an interesting subgroup of symmetric group called alternating group and conjugacy classes in there and some other interesting results. So let's start today's session. First of all, we recall what is a symmetric group. So to define a symmetric group for a given fixed natural number n, and the symmetric group, this is denoted by Sn. This is the set of all permutations of the set In, that is first n natural numbers, we can say. So if we want to define a permutation group, first we need a natural number n, and then we collect all the permutations or all the bijections of this n objects or n digits. So obviously, the order of the symmetric group Sn is factorial n. Now we have Kelly's theorem, which we have already studied in the session based on group action. So Kelly's theorem says that any finite group of order n is isomorphic to a subgroup of Sn. Kelly's theorem is useful to identify the number of groups for a given order n up to isomorphisms. So if we denote the set 1 to up to n by In and a permutation sigma, which is in Sn. So this sigma is a map from In to In. It is a bijection, and two-line notation is denoted by this. So one is mapped onto sigma 1, 2 is mapped onto sigma 2, and n is mapped onto sigma n. So in this way, you can say that this is 1, 1 as well as onto. Now for a given permutation sigma belongs to Sn, what is the cycle of length k? So sigma belongs to Sn is called a cycle of length k if it permutes k distinct elements cyclically. That is, we can have A1 to AK and they all are distinct from In, and sigma of sigma of A1 is A2, sigma of A2 is A3, sigma of A3 is A4, and so on. And the last one, sigma of A1, that will be mapped onto sigma of An, that will be mapped onto A1, following the rule of cyclicity here. So in compactly, we can say that sigma of Ai is Ai plus 1 if I varies from 1 to k minus 1. And what is sigma of AK? That is A1. And for other AJs, sigma will work as identity. Okay. For example, we can take this 1, 2, 3, 4, 5. So obviously this will be in S5 and it's mapped onto 2, just 4, and 4 is say 1. 3 maps. 3 and 5 is image of 5 is 5. So this can be written as 1, 2, 4. Because sigma of 3 is 3 and sigma of 5 is 5. So if we write this sigma in this form, then we can say that sigma is a cycle of length 3. So obviously here what we can see, 1 is mapped onto 2, 2 is mapped onto 4, and 4 is mapped onto 1 again by cyclicity. So this is the meaning of cycles in a given permutation, symmetrical. Symbolically, we write it as sigma as A1, A2, An, and comma should not be there. Okay. There is a special type of cycle. So if we have cycles of length 2, then those are called transposition. Okay. And there is a result that any permutation in Sn can be written as a product of disjoint cycles. That is, if we have a permutation in Sn, then we can write it as a product of disjoint cycles. And uh, that product will be unique up to reordering of the product. That is this one. So this is a permutation in S5. Here 1 is mapped onto 1. So that is fixed. We will not write that in the cycle form. And 2 is mapped onto 4. 4 is mapped onto 5. 5 is on 3 and 3 is on 2 again. So if we write this in a cycle form, so this will be 2, 4, 5 and 3. And this cycle is sufficient to figure out the sigma. Okay, so if we have this say one line notation, then we can find how any I belongs to I5 is mapped onto I5. Now, what is the meaning of the term I said uniqueness of this product of disjoint cycles? So there, if sigma is A1, A2 to AK, then it can be written as A2, A3, AK, and then AK minus 1. Okay, that is, if we preserve the cyclic order, then we can rewrite it. Okay, but all the forms are same. They represent a same permutation sigma. Okay, and we say that two permutations are disjoint if these two sets are disjoint. That is, I belongs to In, for which sigma of I is not I, and I belongs to In, for which tau of I is not I. That is, if we exclude those numbers from In or those elements from In, whose images are fixed under sigma and tau, then the remaining set, that is for sigma, the subset of In, and that subset for which sigma doesn't work as the identity. And this is the subset of In for which tau doesn't work as the identity. So these two sets are disjoint. So if these two sets are disjoint, then we say that the permutation sigma and tau, they are disjoint permutations. Now, there is an interesting proposition that if we have two disjoint uh, permutations in Sn, then they will commute with each other. Using this proposition, we have a theorem which says that every permutation in Sn can be written as a product of disjoint cycles. And yeah, this product is unique up to reordering, we can say. So we can say that for all sigma belongs to Sn, there will uniquely exist a collection of disjoint cycles, say tau 1 up to tau k, such that sigma is the product of these tau i's. Okay. And yeah, as this cycles are disjoint, they will commute with each other. And as they will commute, so we can reorder this tau i's. Okay, but they will represent the same. So this is the meaning of the uniqueness here, like unique up to reordering. To understand this, consider this example. So here we have 9 elements in In. So this is a permutation in Sn 9. Now see, we start from the first element 1, which is mapped onto 4, and 4 is mapped onto 3, and 3 is mapped onto 1 again. So here the first cycle completes, and the first cycle will be 1, 4, and 3. That is 1 is mapped onto 4, 4 is mapped onto 3, and 3 is mapped onto 1 again. Okay. Now start with the uh, like the smallest element which is not a part of this cycle, which is 2 here. So we start from 2. 2 is mapped onto 7. So we write 2 and then 7. Now we will write image of 7. So 7 is mapped onto 5. So we'll write here 5, and 5 is mapped onto 2. So we will reach at the initial element again. So the cycle will be closed here. So 2, 7, 5, this is the second cycle. And the product, like product of cycles for this permutation sigma. Then uh, the least element which is not a part of these two cycles. So clearly that is the element 6, and 6 is mapped onto itself. So we will write 6 here. That's it. Like, yeah, this is a trivial kind of cycle, we can say. Uh, and then we'll start from 7 because, sorry, 7 is part of second cycle. So not 7, 8. And 8 is mapped onto 9, and 9 is mapped onto 8. So last cycle will be 8 and 9 because here we have included all the 9 elements of I9. Okay. So in the cycle decomposition of sigma, we have 4 cycles. Uh, 2 are of length 3, one is of length 1, and one is of length 2. So what is length of a cycle? So actually the elements in a cycle, number of elements in a cycle will be the length of the cycle, we can say. And what if we replace the term cycles by the transposition? So yeah, we'll see that. Uh, so every permutation sigma belongs to Sn is a product of disjoint transpositions. That is cycles of length 2. So as we can represent a given permutation to a disjoint, to a product of disjoint cycles, yeah, we can represent a given permutation as a product of disjoint transpositions, but the product is not necessarily unique. Mm, Wait, and as well as not necessarily disjoint. Because see, we have this 1, 3, and 5. So this will be written as 1, 5, and then 1, 3. So what is the simplest way to return a given permutation in the form of product of transposition, where the transpositions are not disjoint? So suppose we have this 1, 3, 2, 7. Say this. Then what we will do? We will write first and the last, that is 1, 7. Then we will write first and the second last, that is 1 and 2, and then first and this. Until we didn't uh, reach close to the starting point. That is, if we have this permutation A1, A2 up to AK, then what we will do, we'll write as A1, AK, then A1, AK minus 1, A1, AK minus 2, A1, A3, A1, A2, and then we'll stop. So in this way, we can see that if we have a permutation or if we have a, we can say this is a cycle. So if we have a permutation where k elements are appearing, k elements of Sn, then it will be written as the product of k minus 1 transposition. Okay. And if we want to find out the number of transpositions ij, where I and j, they rise between 1 and n. Here this n is the number for which we are computing the symmetric group, that is Sn. And I is strictly less than j. The number of such transpositions are n into n minus 1 by 2. So you can see that these are the upper triangular elements. If we write the square matrix uh, like ij, if we write this matrix, where this I represent ith row and j represent jth column. Now, what is simple transposition? So, simple transposition is a transposition where the second, like second element in the transposition is exactly one greater than the first. Okay, so these are the transposition of the form I plus 1, where I is greater than or equal to 1 and this is less than n. Less than n, otherwise like we cannot have n plus 1 there. And any given symmetric group Sn can be generated by simple transpositions. So if we have all the simple transposition, then we can generate the symmetric group Sn. And suppose we have In and we have two elements K and L with this ordering, that is 1 is less than or equals to K, which is less than L, which is less than or equal to N. Then this transposition KL, this will be written uh, like this. That is, we start from K and then we increase the second element in the transposition by 1. That is K plus 1. Then we will write the last element of the first transposition in the first element of the successive transposition. So this will be K plus 1. And this element will be 1 greater than this. So this will be K plus 2. Then the third transposition in the form will be K plus 2, K plus 3. We will continue the product like this, and then we will reach up to this transposition L minus 1 L. And after that, we uh, decrease it to reach up to this K again. But note that here all the transpositions are simple transposition. Okay. So the second one, what we can do for the like successive transposition of this transposition L minus 1 L, we will write this, uh, we will focus on this L minus 1. And what is, what element will make this simple transposition? So that will be L minus 2. So we will write here this transposition L minus 2, L minus 1, and then L minus 2, L minus 3, until we will get K here. So this will be the last transposition of this product form will be K plus 1. So if we have any permutation, if we have any transposition in particular, say KL, where this L is greater than K, then we can write it as a product of mm, simple transpositions. For example, in S4, we took a transposition 1, 4. So how to write it as a product of simple transposition. So we'll start from this 1, then we write 1, 2, 2, 3, 3, 4. So now in 3, 4, the 4 is the mm, the second element in the transposition. So we'll stop here and then we'll start to decrease it. We will write 2, 3, or the next transposition will be such that the second element in the transpositions should be the first element of this. And making it a simple transposition. So obviously the element or the transposition could be 2, 3, then 1, 2, and then we'll stop it. So if sigma, which is a permutation in Sn, and if we write it as tau 1, tau 2 up to tau r as the cycle decomposition, then what will be the sign of sigma? Sign of sigma will be -1 to the power r, where r is the number of disjoint cycles in the cycle decomposition of the given permutation sigma. So whenever we need to calculate the sign of a given permutation, first we will write it in the cycle decomposition form, and then the sign of that permutation sigma will be -1 to the power number of disjoint cycles in the cycle decomposition of sigma. So this is the way we can figure out the sign of a given permutation. Now, what is the sign of identity? So identity, which is say E, which is tau 1 up to tau r. Here we write it as product of some transpositions because the cycle decomposition form that will not be so convenient. So here r will be congruent to 0 and a modulo 2. Now, okay, and we saw that a given permutation can be written as two different form of product of transposition. So suppose sigma is tau 1 up to tau r. This is the first transposition decomposition, we can say. And another one is tau 1 to tau, sigma 1 to sigma s, where this tau r, tau I and sigma j, they are transposition. So R will be congruent to S modulo 2. Now, what is an alternating group? Alternating group is a subgroup of symmetric group. So if we have Sn, that is a symmetric group of order n, like order I'm saying with respect to this fixed element n, otherwise the order will be factorial n. So the subgroup of this Sn, we have an interesting subgroup that is An, which is known as the alternating group. And what is the alternating group? So a permutation will be an element in the alternating group if and only if that permutation can be written as a product of even number of transposition. That is, the subgroup of all even permutation will be the alternating group. Now, we want to study the conjugacy class in symmetric group. So if we have some sigma, which is A1 up to AK, and tau, which is in Sn, then tau sigma tau inverse, this will be calculated as tau of A1 up to tau of AK. And here we will say this sigma and tau sigma tau inverse, they are conjugate to each other. And if we write sigma belongs to Sn as sigma equals to sigma 1 up to sigma r, say this is cycle decomposition of sigma, where length of sigma 1 is less than or equals to length of sigma 2, which is less than or equals to up to length of sigma r, then the cycle type of sigma is written as this: L sigma 1, L sigma 2 up to L sigma r. This can be written as this form also: 1 to the power m1, 2 to the power m2 multiplied by up to k to the power mk. Here, mi is number of I cycles appears in R. Obviously, the sum of all these Li's will give us N. And we say two compositions, tau and sigma, have same cycle type if cycle type of sigma is same as the cycle type of tau. Now, I would like to explain in this with an example. So, okay, let sigma is 1, 2, 3, 4, 5, 6, 7, 8. And 1 is mapped onto 2, 2 is mapped onto 1, 3 is mapped onto 3, 4 is mapped onto 6, uh, 5 is mapped onto 7, 6 is mapped onto 8, 7 is mapped onto 4, and 8 is mapped onto 5. So the cycle decomposition for the sigma will be, we'll start from 1 and 1 goes to 2, 2 goes to 1 again. So this will be the first cycle. Next, 3, okay. Then 4 goes to 6, 6 goes to 8, 8 goes to 5, 5 goes to 7, and 7 goes to 4. Okay. So the cycle type of sigma will be, okay, so first we will reorder this. Say this is 3, 1, 2, 4, 6, 8, 5, and 7. So this is sigma 1, this is sigma 2, this is sigma 3. And length of sigma 1 is 1, length of sigma 2 is 2, and length of sigma 3 is 5. So, yep, length of sigma 1 plus length of sigma 2 plus length of sigma 3, that is 1 plus 2 plus 5, that is 8. And yep, that is true as we take an element of is 8. And what is the cycle type? Cycle type of sigma will be now L of sigma 1, L of sigma 2, L of sigma 3. That is 1, 2, 5. And what if we have something like this, some sigma like 1, 2, 3, 4, 5, and 6, 8, 7, then cycle type will be Now this will be sigma 1. Now sigma 2. So we have two cycles of length 2. There is no problem. Either this can be sigma 2 or this one. Okay. And now this will be sigma 4. So the cycle type will be 1, 2, 2, and 3. Okay. Now what is conjugacy in Sn? So two cycles, sigma and tau, they are said to be conjugate in Sn if and only if length of sigma is same as length of tau. Okay. So if length of what is length of sigma? So if sigma is written as a1, a2 up to ak, then this k will be length of sigma. So we can say that any two cycles of same length, they will be conjugate, and any two cycles will be conjugate if they have same length. Now, two elements, sigma and tau, they are conjugate in Sn if and only if their cycle types are same. So this theorem is very important to figure out the conjugacy classes in Sn. So whenever we need to find the conjugacy classes, uh, that is the number of elements which are congruent to each other, we need to find the cycle types in the given symmetric group. And number of conjugacy classes in Sn, they are same as the number of cycle types in Sn, and that is same as the partitions of n. Uh, I would like to explain this by an example. So what is number of conjugacy classes in S4, or what are the possible cycle types in S4? So they will be the number of partitions of 4. So 4 has these 5 partitions, that is 4, then 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. So we have these 5 partition, like number of partitions will be 5 for this 4. So S4 has 5 conjugacy classes, or we can say that S4 has 5 types of cycle types. Okay. So this partition will represent the cycle type, this 4. Note that here this 4 is not the mm, permutation. This is a cycle type. Okay, write it. And this 3, so here we will have 1 comma 3, because we will write the least first. Okay. And this, so 2 comma 2, no problem. This will be 1 comma 1 comma 2. We will write the same number, mm, like in multiple times if that is repeating in the partition. Okay. Now this is 1 comma 1 comma 1 comma 1. So these are 5 possible cycle types for S4. Now what is conjugacy in AN? So if n is greater than or equal to 5, that is we are working for Sn where n is greater than or equal to 5, and sigma and sigma dash, they are two different uh, three cycles in Sn. 3 cycles means cycles of length 3. Then sigma and sigma dash, they will be conjugate. That is, sigma dash can be written as tau sigma tau inverse for some permutation tau in An. So yeah, obviously tau inverse will exist because An or Sn has bijective maps on IN. Okay, so this is like simply I want to explain this by like sigma and sigma dash uh, conjugate in Sn if sigma dash will be written as tau sigma tau inverse for some tau belongs to Sn, and sigma and sigma dash they are said to be conjugate, or they share the conjugacy class in An if sigma dash is tau sigma tau inverse for tau belongs to An this time. Okay. Now, what is simplicity of An? That is whether An are simple groups or not. So, what is a simple group? A group is said to be simple if it has no proper non-trivial normal group. That is, some group G will be simple if it has only two normal subgroups, the identity and the group G itself. So what are the cases for An to be a simple group? So if we have A1, uh, that will be only the identity map. So yeah, that is simple. And A2, that is also simple. What about A3? So A3 is isomorphic to this Z mod 3Z. This is a simple group, but A4 is not simple because A4 has a special type of subgroup. A4 is unique in this sense. So uh, this group of four elements, this is identity element, then mm, elements who are product of disjoint transposition. So 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. These four elements, so here this is an element of order 1, and these three elements have order 2. So this group is isomorphic to Kleen's 4 group, and this is normal in A4. And An, this is simple for all n greater than or equal to 5. Alternatingly, we can say that for Sn, where n is greater than or equal to 5, An is the only non-trivial normal subgroup of Sn. Why? Because An has index 2 in Sn. So An will be normal in Sn. Now, what is sign map, which is used to define the alternating group? So we have already discussed the notion of sign map in previous session, but I would like to recall it. So if Sn is a symmetric group for In, then a sign map is a map from Sn to this +1 and -1. That is a group isomorphic to Z2, you can say. And if sigma belongs to Sn, then the sigma acts on Rn by permuting the coordinates by the permutation sigma. So we can have a map tau from Sn to GL and R, that is a general linear group over R. So this is an injective group homomorphism, and it maps every sigma to tau sigma. And the sign of the permutation sigma will be the determinant of tau n. Okay. So actually, what is the tau n and how we can find the determinant? So this is the way to determine tau sigma. Tau sigma, that is the permutation matrix which is associated with the permutation sigma. So for this, we need to find out the standard basis for Rn, which is E1, E2 up to En, and tau sigma with respect to the standard basis B. This will be uh, this matrix where the first column will be E sigma 1. Here this sigma 1, that is the image of 1 under sigma. So here we will get some EI. So here we will write the ith element in the basis standard basis of Rn. Okay. There is another definition for this sign map. So this is the Van der Moot matrix, and its determinant, if that is some delta, where this delta is actually this product x1. Here we are writing this x1, x2 up to xn as n commuting variables. So what is the way to define the sign map? So if we have some sigma belongs to Sn, then what will be sigma delta? Sigma delta will be uh, here we will write, okay, so we need to write it as this. So this is x. So this is in the place of indices, we will write sigma I and sigma j. So sigma of, we can see that sigma of delta, this is either delta or minus delta. So what is the way to define the sign map? So there are some observation, that is this delta contains these type of vectors xi minus xj for each I less than j, and for I less than j and sigma belongs to In, this xi minus xj, this can have two possibilities. First, with respect to sigma I less than sigma j, and second one is for sigma of I is greater than sigma of j. So what we do, we collect this possibility, because in delta we write xi minus xj where the first index is less than the second one. Okay, so if we take the permutation sigma and the role reverse, then what we do, we form this an, where this an is the collection of the pairs ij from in cross in, where I is less than j, but their maps, that is sigma I and sigma j, they have the reverse order. That is for I less than j, sigma of I is greater than sigma of j. That is, this is the set of inversion. So we can split the sigma of delta in these two parts. In first one, we have sigma of I less than sigma of j for I less than j. And in the second one, we have sigma of I is greater than sigma of j for I less than j. So we can see that this part, this will contribute to uh, powers of -1. So um, here what we can do, we can write -1 and then sigma of, sorry, let me write it. Each factor can be written as minus 1 into x sigma j minus x sigma I. And then we will take the product. Okay. So we will have this minus 1 to the power something, and that will be cardinality of the set AN. Okay. So collectively, we can say that sigma of delta is minus 1 to the power cardinality of A sigma into delta. So here, this part, minus 1 to the power cardinality of A sigma, this is the sign of the permutation sigma, which can be denoted by this also, epsilon of sigma. So this is an example. Here what we have this delta for n equals to 4. That is, we will write all xi minus xj, where I is less than j and I and j varies from 1 to 4. So we have these 6 factors. Okay. And if we have this sigma 1, 2, 3, 4, which can be written in this form, so what will be sigma of delta? This one will be sigma of 1, this 2 will be sigma of 2, that is x1 will be now x2 and x2 will be now x3. So we can write uh, the form of sigma delta, where we have these 6 factors. So this will be minus 1 cube delta, which are coming from this, this, and this. So here, if we write the indices in the ascending form, then we can have minus 1, and minus 1, and then we will have the product delta. So this is minus 1 delta. That is, this is minus 1 um, times delta. So the sign is minus. And we can verify this by the definition. So if we decompose the permutation in cycle form, so here we have 3 cycles, we can say. So this has a sign minus 1. So if sign is 1, the permutation will be even. If the sign is minus 1, then the permutation will be odd. This is an application of we can say the sign map or the determinant. We like the determinant of the matrix we used to compute the sign map. So in this way, if we have an n by n matrix of some field F, then we can find the determinant of that matrix using the sign map. And this is an example in S3. So using the sign maps on S3, we can find any, we can find the determinant of any 3 by 3 matrix where this entries are coming from some field. Say they are coming from the real field. Now consider this question. We have 2 permutations in S5, sigma and delta, and we need to write the cycle decomposition for this. So let's do it. Sigma is 1, 2, 3, 4, 5. 1 goes to 3, 2 goes to 4, 3 goes to 5, 4 goes to 2, and 5 goes to 1. And what is tau? That is 1, 2, 3, 4, 5, and 1 goes to 5, 2 goes to 3, 3 goes to 2, 4 goes to 4, and 5 goes to 1. So cycle decomposition of sigma, we will start from 1. 1 goes to 3, 3 goes to 5, and 5 goes to 1. So here the cycle completes this. And now 2 is remaining. So 2 goes to 4 and 4 goes to 5. Sorry, 4 goes to 2. So this is done. So this is the cycle decomposition of sigma. Now, what is the cycle decomposition of tau? One goes to 5. So we will write 5 after 1. 5 goes to 1. So first cycle completes. Then 2, which is not in the first cycle. So 2 goes to 3. So we write 3 after 2. Then 3 goes to 2. So this cycle also completes. And 4 goes to 4. So if you want to write this will be 4. Now, to find cycle decomposition of sigma square, first we need to find what is sigma square. So sigma square is sigma into sigma, that is 1, 2, 3, 4, 5, 3, 4, 5, 2, 1, 1, 2, 3, 4, 5, and 3, 4, 5, 2, 1. So now we need to compute the product. So see, here 1 goes to 3 and here 3 goes to 5. So here we will have 5. 2 goes to 4 and 4 goes to 2. 3 goes to 5 and 5 goes to 1. 4 goes to 2 and 2 goes to 4. 5 goes to 1 and 1 goes to 3. Okay. So what is the cycle decomposition? That is 1, which is mapped onto 5. 5 is mapped onto 3 and 3 is mapped onto 1. So 2 goes to 2 and 4 goes to 4. So this is 2, this is 4. Okay. See, there is a trick to find cycle decomposition for sigma square if we have the cycle decomposition of sigma. So again, sigma is 1, 3, 5, 2, 4. What will be sigma square? Okay, so here we can see that 1 is mapped onto 3 and 3 is mapped onto 5 and 5 is mapped onto 1. So in the first cycle, what we will do, here actually in the cyclicity, uh, we are writing the image as the first element coming after the element. Okay, so that is if we have 1, we write the element like just next after 1. Okay, so yeah, I'm writing this 1, 3 and 5. So this is the cycle actually in this form. Okay, so 1 and the next one is 3. Okay, but what if we skip it? So here actually we have sigma to the power 1. So we are writing just next element. But if we want to find sigma square, then we will write the second element. Okay, That is, what will be the image of 1? The image of 1 will be the second element. These three, this is first element in the cycle coming after 1, and the second element coming after 1 is 5. So this will be 5. Now, what is the image of 5? Image of 5 will be the second element coming after 5. That is, we won't write this one after 5. We will write 3. And what about 3? So after 3, the second element is 1 again. So yeah, the cycle completes. Now what about these? This cycle, 2, 4. So here, actually, we have only two elements in the cycle, 2 and 4. So 2 is mapped onto 4. So after 2, we have 4. After 4, we have 2. After 2, we have 4 again. So if we want to find out sigma square, what will we will do for this cycle? So what will be the image of 2? Image of 2 will be second element if we run the cycle. So at the first place, we will have 4, but we find out the second element. So that will be 2 again. So we need to close the cycle here. And what about 4? So for 4, we will start from here. First element will be 2 in the cycle, and the second one will be 4 again. So that's why we have 4 here. Okay, and yeah, we can check that both are same. So this is a shortcut to find it. I'm erasing this. Mm. Third one, yeah, fourth one. Okay, sigma tau, that is 3, 4, 5, 2, 1, and here we will have 5, 3, 2, 4, and 1. Okay, so this will be 1, 2, 3. So sigma tau means this is actually sigma tau of some I, which is sigma of tau of I. I belongs to IN, and here N is I actually. So it means that on any I belongs to I5, first we will apply this tau, and then we will apply sigma. Okay. So this is sigma, this is tau. So what will be the image of 1? First, we will find the image of 1 under tau, and then we will find image of that image under sigma. So 1 maps to 5 and 5 maps to 1. So this is same. 2 on 3, 3 on 5, 3 on 2, 2 on 4, 4 on 4, 4 on 2, and 5 on 1, 1 on 3. Yeah, we can see this is another permutation. This is biject. So cycle decomposition of sigma tau, this will be 1, 2, 5, 3, 4. Okay. Last, tau sigma. That is 5, 3, 2, 4, 1. And here we will have 3, 4, 5, 2, 1. So this will be image of 1 will be image of 3, that is 2. And 2, 4, 4, 4. 3 on 5, 5 on 1. 4, 2, 2, 3. And 5 goes to 1, 1 goes to 5. So cycle decomposition of tau sigma, this is 1, 2, 4, 3, then 1, and this is 5. Okay, so this is the cycle decomposition for tau sigma. Mm, I would like to do one more thing. Mm, what is the short trick to find the cycle decomposition of tau and sigma if we have the cycle decomposition of tau and sigma both? So what is tau? Tau is 15234. What is sigma? Let me write it here. 13524. Okay. Therefore, what is tau sigma? Okay. So for tau sigma, it starts from 1. So see, in tau, 1 maps to 3, and because first we will apply tau and then we will apply, sorry, first we'll apply sigma and then we will apply tau. So 1 goes to 3 and 3 goes to 2. So here we will write 2. Okay. Now come to the element 2. So 2 goes to 4 and 4 goes to 4 again. So here we will have 4. Okay. Now what about 4? 4 goes to 2 and 2 goes to 3. So here we will have 3. Okay. Now image of 3. So 3 goes to 5 in sigma, and in tau 5 goes to 1. So the next element will be 1, which is already written here. So the cycle will be completed. So that's it. Okay, now the remaining element is 5. Come to that. 5 goes to, sorry, 5 goes to 1 and 1 goes to 5. It means the image of 5 is 5 under the composition of tau and sigma. Okay, So this is another way to compute cycle decomposition of the composition element tau sigma. Okay. Similarly, we can find sigma tau. Let's check whether this is same or not. But here, note that first we will like consider the images under tau and then under sigma. Okay. So let's start from 1. 1 goes to 5, 5 goes to 1. So here we will write, sorry, not 1 goes to 5. 1 goes to 5 and here 5 goes to 1. So the first element will be 1 as it is, then 2. So 2 here, 2 goes to 3 and 3 goes to 5. So after 2 we will write 5. Then 5 goes to 1 and 1 goes to 3. So here we will write 3. Now 3 goes to 5 and 5 goes, sorry, 3 goes to 2 and 2 goes to 4. So here we will write 4 and 4 goes to 4 and 4 goes to 2. So the cycle completes. Okay. So you can check uh, these are, these two are same. This one and this one. And this, they are same. Okay. Now I would like to do one question. Let what if a permutation is given in cycle decomposition? Say 1, 3, 2, 4, 6, 9, 5, 7, 8. Okay, that's it. Then find sigma square and sigma cube. Okay. So what will be sigma square? See, if we have sigma, 1 goes to 3, 3 goes to 2, 2 goes to 4, 4 goes to 3, 6, 6 goes to 9, and 9 goes to 1. That is, in the cycle, we write just next element there. Okay. But if we skip one element, that is after 1, we write this 2. After 2, we write 6. After 6, we write, okay, we will have to leave this 9 and we will go to 1. Okay. But see, 6 and 4, they are meaning. So 3 goes to 4, 4 goes to 9, and 9 goes to 3. Okay. So let's write it. The element will be, let me erase this. One, 2, 6, and 3, 4, 9. What about this? 5 goes to 8, 8 goes to 7, and 7 goes to 5. Yes. What is sigma cube? So now we will have to skip 2 elements, or we'll have to write the third element in the cycle. So what about 1? 1 will be mapped onto 1, 2, 3. So this time 4. 4 is mapped onto 1, 2, 3. That is 1. This will be this. And now what about 3? 3 is mapped onto, okay, let me erase this. 3 is mapped onto 6. 6 is mapped onto 1, 2, and 3. What about 2? 2 is mapped onto 9, and 9 is mapped onto 1, 2, and 3. That is 2. Okay. What about the second cycle? So, see, after 5, this is the first element, this is the second element, and this is the third element in the cycle. So 5 will be mapped onto 5 itself. Similarly, 8 and 7. Okay, wait. I considered this one. We need to consider this, but still, 5 will be mapped onto 1, 2, and 3. That is 5. 7 will be mapped onto, we'll have to leave 8, we'll have to leave 5. So this will be 7 and 8. They can be seen. Okay. So this is sigma square and this is sigma cube. Now we have two permutations in S7 and we need to find their inverses. So how to do this? This is sigma. So sigma inverse will be, again, we will have images of these 11 elements. See, here we have this I is mapped onto sigma I, for I belongs to I7, that is 1, 2, 3 up to 7. And this sigma is bijective. So here we can have sigma inverse of I, that will give us I again. So we will apply the inverse map here. Okay. And this will be, see, in the inverse map. So here, this is the element in the domain, and this is the element in the codomain, we can say. So, or this is the image, and mm, now this is actually sigma inverse of sigma of I, which is I again. So this image is basically an element of the domain for the inverse map. And here the element in the domain is the image under sigma inverse. Okay. So here, if one is mapped onto 2, then we need to consider this in a reverse way. Okay. That is, if 1 is mapped onto 2 or image of 1 under sigma is 2, then the image of 2 under sigma inverse will be 1. Okay, so this will be 1. And like alternatingly, if we want to find out the image of 1, so here, like this is domain, this is codomain for sigma. And for sigma inverse, this will become the domain and this will become the codomain. So for 1 belongs to domain, the image will be 5 under sigma inverse. Okay, so here we will write 5. Now, image of 2 will be 1. Image of 3 will be 6. Image of 4 will be 2. Image of 5 will be 7. Image of 6 will be 3. And image of 7, no? So image of 7 will be 4. Okay, so this is the way to compute sigma inverse. Now, what is cycle decomposition for these two? So this is same as 1, 2, 4, 7, 5. 3 is remaining, no? 3, 6. That's it. 1, 2, 3, 4. Okay, 6, 7. What about this? So this is 1, 5, 7, 4, 2, and then 1. And 3 mapped onto 6. Okay. So how to write this in cycle decomposition form? Again, sigma is 1, 2, 4, 7, 5 into 3, 6. Therefore, sigma inverse will be inverse of this. 1, 2, 4, 7, 5, 3, 6. Okay. So here, to find the inverse of this product of two cycles, what we will do, we will compute the product of inverse of this cycles. Okay, that is inverse of this cycle 1, 2, 3, 4, 7, 5. This will be 5, 7, 4, 2, 1. We write this in the reverse order actually. And what about 3, 6? So 3, 6 will be 6, 3. So are they same? So yes, actually we focus on the order. Okay, so here we have 1, 5, 7, 4, 2. So 1 maps to 5, 5 on 7, 7 on 4, 4 on 2, and 2 on 1 again. And 3 on 6, 6 on 3. So yeah, they are same. Okay, so this is a shortcut to compute the inverse. Similarly, we can find the inverse of tau. So I'm leaving that for you. Now find the order of this permutation. Okay. So this sigma, this belongs to actually S10. Okay. What does it mean? Actually, we need to find okay. We need to find the smallest n, the smallest natural number, such that sigma of I is I. For all I belongs to I10. So this will be the order of sigma. So yeah, the first way is to find this detailed or in a complex way. But the calculation will be reduced if we consider the cycle decomposition of sigma. Okay. So cycle decomposition of sigma is 1 maps to 4, 4 maps to 6, 6 maps to 3, 3 maps to 1. So this is the first cycle in the product. Now 2 is not a part of this. So 2 maps to 5, 5 maps to 9, 9 maps to 7, 7 maps to 8, 8 maps to 10, 10 maps to 2. So this completes. Now there are 4 and there are 6 elements. So yeah, this is the cycle form. Now, what is the meaning of order? So, see, actually, we need to find sigma to the power n such that we get this 1, 2, 3 up to 10, right? That is, the question is that for the first cycle. So, let's focus on this. So, this is actually what should be the power of sigma, or like how many times we multiply to sigma by itself, so that we can get the image of 1 to 1 again. So consider the cycle which has 4 elements. So sigma, under sigma, image of 1 will be 4. Under sigma square, image of 1 will be 6. Under sigma cube, image of 1 will be 3, and under sigma 4, image of 1 will be 1 again. Okay. And similarly for this 4, 6, and 3. That is, if we have sigma 4, then we will get this 1, 4, 6, and 3. So 4 is such smallest natural number for which we have this decomposition. Okay. 4 is such smallest natural numbers. All the multiples of 4 will give us this cycle. Okay. Now, what about this? So this is sigma 1 and this is sigma 2. So this is sigma 1 to the power 4. That will give us the identity reduced to sigma 1. We can say. Now, what about sigma 2? So here, what is the length of the cycle? Length of the cycle is 6. So if we take sigma 2 to the power 6, then we get like image of 2 as 2, image of 5 as 5, and so on. So here we need sigma 2 to the power 6. So that will be the identity map reduced to sigma 2. Okay. So under sigma 2 to the power 6, we will have the remaining one: 2, 5, 9, 7, 8, and 10. Okay. So what is the question here? We need to find the order for product of these cycles. Okay. So the first cycle will become part of identity map if we have power 4. and the second cycle will become a part of identity if we have power 6. So what we can do, we can take the least common multiple of 4 and 6 to get the least natural number for this product of sigma 1 and sigma 2, that is sigma. Okay. Therefore, order of sigma is LCM of order of sigma 1 and order of sigma 2. That is LCM of 4 and 6. So that is 12. Okay. Now, this one. What is the order of this permutation? So say sigma is sigma 1, sigma 2, sigma 3, sigma 4, where order of sigma 1 is order of 1, 12, 8, 10, 5. There are 5 elements, so this will be 5. But wait, for this, we need to check whether all the cycles are disjoint or not, because only then we can have the cycle decomposition of that. So here, yeah, we can see that this is the cycle decomposition for a permutation in S13. Okay. Order of sigma 2, that is order of 2 and 13 here, that is 2. Order of sigma 3 is order of 5, 11, 7. That is 3. Order of sigma 4, that is order of 6, 9. That is 2. Therefore, what is order of sigma? Order of sigma is LCM of order of sigma 1, comma, order of sigma 2, and order of sigma 3, and order of sigma 4. That is LCM of 5, 2, 3, and 2. Wait, there's something is missing. One, two, three is not there. No? Okay, so 3 is fixed. That case. So what is this? LCM is 30. That is order of sigma is 30. What if the question is given like this? Find the order of sigma, which is this. So clearly this sigma belongs to some Sn where n is actually here also. I should write it as sigma belongs to Sn where n is greater than or equal to 13. Mhm. And here n is greater than or equal to 6. Maybe like it is a part or it is an element of S8 where um, image of 7 is 7 and image of 8 is 8. So that's why I'm writing like this. But here, this form is not the cycle decomposition of sigma, because in cycle decomposition of sigma, we need disjoint cycles. But this 1, 3 and 1, 5, these two cycles are not disjoint. So see, why I'm saying there, sigma is, let me write it again, 1, 3, 2, 4, 6, 1, 5. So this is sigma 1, this is sigma 2, and this is sigma 3. So here, sigma 1 and sigma 3 are not disjoint. Why? Because for sigma 1 is mapped onto 3 and 3 is mapped onto 1, or write it as sigma 1 to the power of sigma 1 of 1 is 3 and sigma 1 of 3 is 1. And sigma 1 of I is I if I is I n minus 1 and 3. Okay. And sigma 2, this is sigma 2 of 1 is 5 and sigma 2 of 5 is 1. That is this also sigma I is I belongs to I n minus 1 and 5. That's it. That is 1 belongs to sigma 1 and 1 belongs to, mm, let's say, 1 belongs to I n such that sigma of 1 is not equals to 1 and sigma of no, sigma 2 of 1 is not equals to 1. But 1 belongs to, like, or I can say 1 is in both cycles. Okay. Therefore, sigma 1 and sigma 3, they are not disjoint. Uh, this actually. Here you can relate. 1 belongs to In such that sigma 1 is not uh, 1 and 1 belongs to In such that uh, sigma 3 of 1 is not equals to 1. That is not 5. Okay. So that's why sigma 1 and sigma 3, they are not disjoint here. So what we will write, we will make the given permutation in its cycle decomposition form. Sigma is 1, 3. 24615. So this can be rewritten as we need to check whether these two commutes or not. So I will prefer to write it as this. Okay, so this is 15 and 246. So this can be written as 153 246. Okay. So now this is a cycle decomposition form for the permutation sigma. So we can say order of sigma is order of 153 and order of 246. So this will be 3. Okay. Now compute the determinant of the permutation matrix associated to this permutation. So how to solve this? Let sigma is 1, 4, 2, 2, 3, 1, 4, 5, and 5, 3. That is sigma 1 is 4, sigma 2 is 2, sigma 3 is 1, sigma 4 is 5, and sigma 5 is 3. Therefore, the permutation matrix associated to sigma is, so see, this is an element of S5. That is, we need to find the standard basis of R5. Mhm. Which is E of sigma 1, E of sigma 2, E of sigma 3, E of sigma 4, and here I will write E of sigma 5, where B is E1, E2, E3, E4, E5 is the standard basis of R5. So this one will be E sigma 1, that is E4, comma, E2, E sigma 3, that is E1, E sigma 4, that is E5, and E sigma 5, that is E3. So this is actually the matrix 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0. Okay. So we need to find the determinant of this. What is the determinant? Uh, in the question, the determinant is asked, not the permutation matrix. Okay. What is this? So its determinant will be uh, there are several ways to find the determinant. -1 to the power, we can say the elementary operation to make this identity uh, matrix of order 5 again. So how many such elementary operations are required? We need one here. So this will be the first. And then here we will have E1 and this will be E2. Fine. And this will be E4. This is E5 and this is E3. So these two are done. Here we need E3. So then we will shift them again, like interchange them, or we will apply this elementary operation. And then this will become E3 and this will become E4. But we need E4 here and E5 there. So again, we will use the elementary operation there and this will be +1. That is, we have -1 to the power 3. So the determinant is -1, which should be the sign of the permutation. Or the determinant of this matrix can be found by the sign. So, okay, let's write the cycle decomposition of sigma, which is 1, 4, 5, 3. Okay, 1, 4, 5, 3. 3 goes to 1 and 2. Okay. Okay. So if you want to write this in the form of transpositions, we can say, then this can be written as 1, 3, 1, 5, 1, 4, 2 is mapped onto 2 itself. So sign of sigma, that is -1 to the power 3. We can find out in this way again. So that is -1. Okay. Or like we also know that sign of a cycle A1, A2 up to AK, this is -1 to the power K, either -1 or +1. So that can be used here also. Okay. So this is the short trick to find the determinant of the permutation matrix associated with the permutation, or if you need to find out the permutation matrix, so this will be the permutation matrix. Now find the number of conjugacy classes of S5. Also write the class equation for S5. So what are the conjugacy classes? We know that the number of conjugacy classes of S5 is the number of partitions of 5. So we need to find the partition of 5. First one is 5, then 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and 1 plus 1 plus 1 plus 1 plus 1, 5. There is no other possibility for this. That is, we have 7 partitions of 5. Okay, so number of conjugacy classes of 5 is number of partitions of 5, that is 7. Okay. Now, what are the class types? So this is again an interesting thing to do. Here we have class type as 5. Here we have 1, 4. Here we have 2, 3. Here we have 1, 1, 3. Here we have 1, 2, 2. Here we have 1, 1, 1, 2. And here the class type is all 1. Okay. We have these 7 class types. Now, we need to write the class equation for S5. So, the class equation of S5 will be written as order of S5 equals to summation of order of conjugacy classes of A, where this A varies from, you can say, different conjugacy classes. Okay. It means if we can find out the class types or orders of these 7 conjugacy classes, and we write them in summation form, we can find out the class equation of S7. Uh, sorry, S5. What is order of S5? Order of S5 is factorial 5. That is 120 into something. We need to find it out. So I would like to state a result. Mm, class type of some A belongs to Sn is alpha 1, alpha 2 up to alpha k, then order of the conjugacy class of A, this will be factorial n divided by 1 to the power alpha 1, 2 to the power alpha 2. Should I write it as me confusing? Okay. Okay, fine. I will rewrite it if needed. So here, is the order of these conjugacy classes. So order of these conjugacy classes is this. We will write factorial 5, and then here we have 5 one times, and then we will write 1 factorial. So I will rewrite that. Okay. And for this 1 4, how we will do here, we will write factorial 5, and then 1 to the power 1 and 4 to the power 1 and factorial 1 and factorial 1. This will be factorial 5 divided by 2 to the power 1, 3 to the power 1 and factorial 1, here factorial 1. Here we will write the first number which is coming here. So this is 1 which is coming 2 times. So 1 to the power 2, 3 which is coming 1 time. So here we will write 3 to the power 1 and factorial of power of 1, that is factorial of 2. Here we will write factorial of power uh, 3, that is 1. So factorial of this. Here we will write 5 factorial divided by 1 which is coming 1 time. So this 2 which is coming 2 times, factorial 2. Now, sorry, 2 to the power 2. Now, factorial of these powers. So this is 1 factorial 1, factorial 2. Now this is factorial 5 divided by 1 to the power 3, 2 to the power 1. Here we will write factorial of powers, that is factorial 3, factorial 1. Here factorial 5 divided by 1 to the power 5 and factorial of this power. So actually I just wanted to give you a general formula for this. So corresponding to this, I need to rewrite this. How to say? Mm, This is 1 up to alpha 1 times 2 up to alpha 2 times and n to alpha n times. So this will be 1 to the power alpha 1, 2 to the power alpha 2, and this will be n to the power alpha n, and this will be alpha I belongs to Z positive union 0. It can be 0 also, okay? Because see, in the first one is coming 0 times, 2, 3, and 4, they are coming 0 times. So actually here, what we will write, factorial 5 divided by 1 to the power 0, 2 to the power 0, 3 to the power 0, 4 to the power 0, and 5 to the power 1. And 2, um, factorial of their powers, that is factorial 0, factorial 0, factorial 0, factorial 0, and factorial 1. Okay. So these terms will be 1. Actually, that also. So that's why I wrote only 5 to the power 1 and factorial 1. Okay, so this is the meaning actually. So, okay, we are running out of time. I just wanted to compute this. Okay, so I'm erasing this. Fine, let's calculate this. What will be this? This will be factorial 4. That is 24. This will be 5 into 3 into 2. So, so this will be 30. This will be 20. This will be 20. This will be 15. This will be 10. This will be 1. Okay. So let's check what is their summation. So this will be 0 and 1 bit. So we can write it as 24 plus 30 plus 20 plus 20 plus 15 plus 10 plus 1. See, here only this conjugacy class have only one element. That is S5 have trivial center. Okay. So this is done. How to solve this? Find possible orders in S4 and number of elements of each order. Okay, so that's why we need to find partition of 4. So they are 4. 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. That is, partition of 4 is 5. Therefore, S4 has 5 conjugacy classes. Now, we need to find the orders in S4. Okay, so for that, we need to find the cycle types there. So, what will be the cycle type here? 4. That is, here we have elements of the form this A, B, C, D. Here we will have 1, 3. That is elements of the form just giving examples here. They are not the same. Here we will have, say this is A and then B, C, and D. Because we have 1, 2, 3, 4 in I4, but just to explain, I'm replacing 1, 2, 3, 4 by A, B, C, D randomly. Uh, Class type of this is 2, 2. Class type of this is 1, 1, 2. Here we have 1, 1, 1, and 1. That is, here we have elements of the type A, B, C, and D. Here we have elements of the type A, B, not multiplied, uh, not comma, they will be multiplied. Here we have C, D, and here we have this A, B, C, D. Okay. So what will be orders for these type of elements A, B, C, D, where A, B, C, and D are distinct? So obviously they have order 4. Here we have order. So the first cycle will have order 1. The second cycle will have order 3, and they both are disjoint. So what will be the order of the whole permutation? LCM of order of both the cycles. That is LCM of 1 and 3. That is 1. Sorry, that is 3. Here, what is the order? Order of uh, first cycle and order of second cycle. Both are 2, and then we will take their LCM. So here order will be 2. Here the order will be LCM of 1, 1, and 2. That is 2. Here the order will be 1. That is, the possibilities for orders are 1, 2, 3, and 4. Okay, there can't be any element whose order is greater than 4. Now, how many elements are there? So, number of elements of order 1. So, for that, we will refer to this. So, order of these conjugacy class, or order of elements, or number of elements, or number of permutation who has these this cycle type is factorial 4 divided by, only 1 is coming 4 times, and then 2 to the power 0, 3 to the power 0, 4 to the power 0, we can say. and then factorial of powers, that is factorial of 4, factorial of 0, factorial of 0 into factorial of 0. So this will be this, and this is 1. That is, there is only one element of order 1. That is true for every group because this is the identity element. Now, number of elements of order 2. So for that, we have these two categories. We need to sum them. Okay. So corresponding to this, what we have, factorial 4 divided by 1 to the power 2, 2 to the power 1, factorial 2, factorial 1, plus refer to this. So this will contribute how many elements? Factorial 4 divided by 2 to the power 2 and factorial 2. Okay. This means here we will have 6, and here we will have 3, that is 9 elements. Now, number of elements of order 3. They are factorial 4 divided by 1 to the power 1, 3 to the power 1, factorial 1 and factorial 1. That is 8. Number of elements of order 4, they are factorial 4 divided by 4 to the power 1, factorial 1. That is 6. Okay. Here, it is to be noted that if two elements have same order, then it is not necessary that they belong to the same conjugacy class. They can have same conjugacy class, or the conjugacy classes can be different. Okay. Check whether their sum is order of S4 or not. So 1 plus 9 plus 8 plus 6, that is 24. But what is the class equation of S4? For that, we will write this 1 plus, here we don't write 9 because this 6 elements and these 3 elements are coming from different conjugacy classes. So we will write 6 plus 3. Then 8 plus 6. Or like if we want to write it as 1 plus 3 plus 6 plus 6 plus 8. Okay, so this is the class equation of S4. Okay, so that's all for today's session. We will discuss remaining questions in next session. And yeah, the regular problem solving session for week 12 that is remaining, and that will be the only problem solving session for this course in this semester. And other than the session for week 12, that is on upcoming Tuesday, we will have a live problem solving session, which is an extra session. So I'll try to conclude questions from all the topics um for the course, and that session will be on tomorrow from 11 a.m. So please be there. We will discuss the remaining questions of this session and some other problems and your doubts uh, on the extra session which will be following. So thank you.